Okay. So we are discussing the Fourier transform. So we have this recall. Okay. All continuous function coinciding in the endpoints, and that is you can identify that with P of dou, which is we defined the f hat for n in Z. We defined f hat at n equal to integral 0 to 2 pi 1 by 2 pi. Yes. And we know that this is with respect to the L2 inner product, this is same as this. We defined En to be e power in En, which is En at t equal to e power in. Okay. So there is nothing specific about this continuous function. I mean, it's something more general. Even if you, so we can define this for any, I mean, you can have, see this L2, whatever L2, we defined it to be the closure of this. Sorry, completion of this. And you complete it with respect to that norm 2. Okay. In particular, if you have a Riemann integrable function, which is square integrable, okay, Riemann integrable function which is square integrable, then you can approximate by continuous functions on that. I mean, it's possible to do that, and you can define this for that. I mean, this Fourier transform is well defined for any. Up here, we don't know that. I mean, here we haven't done that. These L2s are this space is made up of functions. But if it is a Riemann integrable function, which is square integrable, then you can define that. Similarly, if you have a Riemann integrable function, which is, if you have just a Riemann integrable function, then also you can define this. But then it may not, I mean, here you have some nice property, it will not be, those properties will not be satisfied. But indeed, you can actually define that. We are concentrating only on this piece for simplicity. Since we are having only, it's not a full course. So we are concentrating on this, and we will point out some of the properties. So then we proved the following. We proved that this f hat and goes to 0 as mod n goes to infinity. And we also proved that this we proved. I mean, maybe I didn't state it properly. Mod f of t dt, the square, is equal to summation. I mean, this is all for continuous functions. Whatever the statement I'm making for continuous function, so you can assume that it is in L2 or whatever. So this is equal to mod f hat n square. Okay. This we proved because since this is maybe I'll write it here. If you have any norm f2, any Hilbert space, norm f2 square equal to summation mod. We proved this, right? Fu. So because of that, this is okay. So in particular, this sequence is bounded and all that we have already seen. Okay. So there are some properties. I mean, using this formula, you can directly compute what is f bar. I don't know how to state all that. It's an exercise. Okay. If you can compute f bar of hat, and that will be, what is it? There are many properties which are exercise. You can see any book. Okay. That will be, you will have a bar here, and you can take I mean, you can take a full bar, and you can take integral is linear. It's a limit of some sum. Okay, integral is a sum of, you have the Riemann sum, so you can take the bar outside the integral. Okay, I mean, the conjugacy is a continuous function, and you can, and it's linear, and you can take it. So because of all this, you get that this is equal to f hat at minus t bar. You can prove that. And then there are many other properties. What I want to, what I need today is the following. If you can integrate from a continuous function. So you can define this f of t equal to integral 0 to t f of t dt. Okay. And assume, because we need at the end points the function has to coincide. So assume that integral 0 to 2 pi f of t dt equals 0. Okay. Then this is a continuous function. This is an integral is a continuous function. Then the f is in C0 to pi. And you can calculate this f hat n. Did I use t here? So it should be s. Of course, ds, and then you have e power minus n t dt. And if you use, I mean, the first term will be 0 because it coincides with the end point, and you will have a minus sign, and then if you can differentiate this and you can integrate this, integration by parts. Okay. So you get 1 by minus in. Yeah, then you have integral e power minus int, and you have ins f of s ds 0 to 2 pi, and you will get 1 by in times f hat. Okay, by integration by parts, you get this. Okay. Similarly, see, the one thing is this even though we are defining for functions on this interval, this Fourier transform is actually defined for something called periodic functions. So it is defined on the whole real line. Okay. I mean, if it is defined on this interval and if it coincides on the endpoint, then you can define it on the whole real line. Okay. And whenever we talk about continuity, we talk about the continuity of that periodic function. Okay. And differentiability, all that, or you can consider this. This will be better. Right? Okay. So if it is differentiable and the derivative is continuous, you assume all the nice properties. Okay. Then, I mean, f is continuously differentiable. F is F is in C1. Whatever I call C1, put it in the down or up, I don't remember. F okay. F is differentiable. I don't want to have a notation. Differentiable and f prime is continuous. You don't need all that, but just I want to make a statement, make a theorem. So then you can compute that f hat. So then what do you want? Then okay. You have the same by the same idea. You have that f hat n equal to 1 by in f prime hat. Right? So you can write, I mean, you can compute this either in terms of this or in terms of that. Okay? And in particular, if f is twice differentiable and continuous, and f double prime is continuous, then f hat n equal to, so minus 1 by n square f double prime hat. And this is a summable sequence. So in particular, summation n in z mod of f hat n is equal to, I mean, 1 by n square summation mod of f prime double prime hat n. And this is bounded by less than or equal to summation 1 by n square into, for any Fourier transform, this is true. F hat n mod of this is less than or equal to integral 1 by 2 pi mod f, I mean, of this ds. which is the L1 norm. Okay. So because of that, I mean, it follows directly from that. So 0 to 2 pi, 1 by 2 pi, f double hat, yes. So this is, I mean, this is just a constant, and this is summable. So this converges. Okay. So this implies, in this case, if f is twice different, so let me write it as a proposition. If f is twice differentiable and f double prime is continuous, then this SNF converges. Okay, where we defined SNF at t equal to summation minus n to minus n to plus n f hat n e power in. You want to say this series, you want to show this series convergent, you have to take the, it's enough to show it's absolutely convergent. Okay, I mean, sorry, f converges uniformly. This is a statement. If f is twice differentiable, and I mean twice continuously differentiable, then SNF converges uniformly. The Fourier sum, whatever you call as Fourier sum, that converges uniformly. And that is just clear from this. You have to take the, I mean, you have to take, I mean, and it converges, and the conversion, I mean, the epsilon or whatever should not depend on this t. But if you take the mod t, mod of this, the t vanishes. There is no t anymore. Okay, and you get this, and it follows from that. Okay, is clear, right? But actually, you don't need twice differentiable. You can actually prove this. If it's differentiable, whenever I say f, it is in the it is continuous function. We are only dealing with continuous function. Differentiable and continuous. F prime continuous. Then also SNF converges uniformly. See, here I am not saying that it converges to F. It will follow soon. It will, after some theorem as a corollary, it will follow. If at all it converges, it should converge to F itself. Okay, it will follow. But here I am only talking about the convergence. The last class we started about we discussed about divergence, not converging at some point, divergence. So here we're only discussing about convergence. Okay. So if f is differentiable, then it is convergent. Oof. So converges uniformly. So I have to worry about this, right? Summation minus NTN f hat, right? Or if you want, mod SNF is, okay? I mean, SNF consists of this series. If you take the mod of that, this will go away. You will have only mod of this. Okay? So I have to worry about this. And this is equal to, because it's once differentiable, this is equal to summation minus NTN 1 by n, maybe mod n, okay? Because there is minus mod n f at n. And here we have something called Cauchy-Schwarz inequality. Okay? Cauchy-Schwarz inequality says the following. Cauchy-Schwarz. It says that, if we, I mean, this is, I mean, it says that If you take in inner product space, this is true. Less than or equal to norm x times norm y. In any inner product space, this is true. And in Rn, this is an inner product, right? If you have x1 up to xn, y1 up to yn, then this is an inner product, summation xi yi. Bar or, I mean, it's just real means it's just summation xi yi. This is an inner product. If you apply that Cauchy-Schwarz here, okay, Cauchy-Schwarz implies this is less than or equal to summation minus ntn 1 by n square times summation minus ntn f hat f prime hat n mod square. Okay, I'm just using the Cauchy-Schwarz in Rn. Okay. Now by taking limit equal to infinity, so I mean this is of course convergent, and this is less than or equal to summation minus ntn 1 by n square times, but then this is integral 1 by 2 pi. I mean, this is just the sum of Fourier coefficient of f prime. Okay, square of the Fourier coefficient of f prime. I have noted here, no? That's yeah. Sum of Fourier coefficient equal to that integral L2 now. Okay, because of that, this is equal to sum of f mod f prime t dt square. Okay, this is just a number depending upon f prime. Okay? And this is convergent. As n goes to infinity, this is convergent. So it follows. And it is uniform. There is no this t here. I mean, there is no, I mean, we don't consider this t is not there. Here there is a t, this is different t. There is no t here. So it's a uniform convergence. Okay. So now we want to prove that it actually converges to f. Okay. To do that, we will discuss more about the convergence of S and F. Before that, we want to discuss the we want to guarantee the convergence without any condition, some convergence. This S and F may not converge, as we have already seen, but then there is something called Sesoro sum. You can average it out, average the sum. If you have a sequence, you can take the average of the sequence, then that also converges. Maybe you have seen this, but let me prove it. Okay? So this is a proposition for any sequence. If xn is any sequence, and the sequence in R, xn converges to x. Okay? And let an equal to summation n equal to 1 to n, k equal to 1 to n, ak by 1 by n. Take the average of this. Okay? Then an converges to x. Okay? So if you have some sequence, then this is called Sesoro sum. Okay? I don't know. That also converges to the same limit. Okay? On the other hand, it need not happen that this converges, that need not converge. Yeah? Excellent. There exists xn such that xn does not converge, but the corresponding an converges. Okay? I mean, you might have seen this, but let's prove it. Have you seen it anywhere in the CNI course anywhere? No. Hmm? Okay. Okay, second is very easy. You can take xn equal to minus 1 power n. Okay. Then it doesn't converge, and if you take the sum, it will be minus 1 by n or 1 by n, that goes to C. Okay. First one. So we have to give an epsilon, we have to find a n. That's what we are doing. Okay. So xn converges to x. Choose, so like xn converges to x. Okay. Choose n epsilon such that xn minus x is less than epsilon for all n greater than or equal to n epsilon. So this n depends on this epsilon. Now we want to find some another n prime epsilon or something for the an. I mean, that may not be less than epsilon, maybe epsilon by something. Okay, let's see. That's also small when epsilon is small. So now we want to talk about an minus x. We want to talk an minus x equal to summation 1 by n xn minus x, and this is less than or equal to 1 by n summation mod xn minus k. K minus x, xk minus xk equal to 1 to n. Okay. 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 So I have the n now. So this is equal to 1 by n into summation k equal to 1 to this n epsilon. I take it up to n epsilon, xk minus x. Okay. I mean, this n epsilon is fixed for this epsilon. Okay. So this number equal to m. Okay. This is fixed for this epsilon. Okay. This number is, I mean, we have to choose a n prime depending on the epsilon. So this is fixed on epsilon. So there is no problem. If you want, you can call it m epsilon. Okay. And plus summation. So k equal to n epsilon to whatever that n. Okay, n. So there is 1 by n outside. Summation xk minus x. Now this is less than or equal to 1 by n. So I take this m epsilon plus, that is each of them is less than epsilon, and there are, I mean, there are less than n terms. I write it n terms, n epsilon. Less than or equal to only I'm writing. So I write it n times epsilon because that will cancel with that n. Now I have to choose a n prime. Choose n prime greater than, of course, n epsilon, and n prime greater than m epsilon. M epsilon may be big, but I show m epsilon, and then I will make it much bigger by epsilon. Is okay, no? Then this is less than n prime. M epsilon is less than n prime times epsilon, and this n is, this is less than, I mean, n epsilon by n is just epsilon plus epsilon, 2 epsilon for all n greater than n. If n is greater than n prime, okay, then when n prime is greater than this, okay, then the m epsilon is less than this n times epsilon, so this is okay. Okay, so we have proved this. Here, here, here. So this is here the sum. There is no sum here. Minus x. this sum minus x. You can take nx here. So each one you have an x. Summation x minus x. Then you have x. It's just sum of xk minus x. You get nx. There are n terms here. X minus xk minus x. Right? Then use triangle inequality. Get this. Okay. So now definition. We know that SNF, before that, SNF at T, SNF is defined to be this, minus NTN, F hat N, e power minus NT. And this is equal to integral over 1 by 2 pi, integral over 0 to 2 pi, dn dn t minus s f of s ds. So before that, let me define the following. Here there is a maybe just this you can define in a more general functions, but let us take continuous function f g in c0 2 pi. Then you can define f star g. Okay. This is equal to integral 0 to 2 pi. I think there is 1 by 2 pi here always. F of f star g. This is the new function. Okay. At t, f of t minus s g of s ds. Okay. You can check easily that this is a continuous function again. Okay. Check. Okay. But then what one needs to check is this is also equal to we just change a variable, but there will be something that you will get. See, if you change the variable, I mean, let me say orally, you check it yourself. Okay, you want to change t minus s to some r or something, then you will get the t minus r here. Okay, then this will get minus dr or something, but then this limits will change. But the limit will change from the so this is t minus t to t2 to 2 pi minus t. So which if you interchange, it will be 2 pi minus t to t. 2 pi minus to t, but you have to remember that this will go outside this integral. I mean, by definition, whenever I write this t minus s, here you can see this t minus s goes out of this interval 0 to 2. But then we have defined the addition to be, I mean, we identify 2 pi plus s, yes. Okay. If it goes beyond s or below s, then we identify that. Okay. Modulo that only this addition is defined. Okay. So if you use that, it will follow this. This will follow. Maybe you get it as two integral, you can sum it and make you can. I mean, it will be from 0 to t and t to 2 pi or something, whatever. You can check it. Okay. So this is true. So what we have is Sn of f is nothing but dn star f. Okay. And which is also equal to f star g. Now, the claim is definition. This is what is called Fejer curve. So this is sigma n of f at t equal to summation n equal to 0 to n Sn. There's a 1 by n, so there should be 1 by, no, let me put 1 by n and put minus here. There should be n terms. So Sn of F. This is definition. This is just the Cesaro sum of this SNF. So SNF may not converge. We will prove that this converges uniformly. Okay. So whenever SNF converges, it has to converge to, I mean, we will prove that sigma NF converges to F uniformly. So if SNF converges, it has to converge to that F only. So in the earlier theorem where we proved some uniform convergence, it has to actually converge to F. So before doing that, let me, I mean, this is a more general statement than this. So let me make a more general statement. This is a definition again. Here, let's write it there. Can you see from there here? This is another definition. A sequence of function. I mean, this can be more generally defined as functions in L2 or something, but here for us, we use only continuous function. And what we are getting is also continuous. A sequence of function, but I generally say sequence of n equal to 1 to infinity is said to be an approximate identity. If it satisfies the following three conditions. One, why we say approximate condition to follow from the proposition. Okay, here I am only listing the property. 1 is G n P is greater than or equal to 0 or T. And 2, integral 0 to 2 pi G and T is equal to 1. Third condition is integral epsilon to 2 pi minus epsilon. Okay. G and T. You need mod or something. I think mod is there. Let us see whether mod is needed. I'm not sure. I think mod is needed. Okay. But here it's greater than 0. So this is what is called an approximate identity. Okay. So the idea is we want to prove that this is an approximate. We want to make a, I mean, we want to prove something more general, and then prove that this is also an approximate identity. So this will also satisfy the same. So proposition is a problem. Given as an approximate identity. Then Gn star F converges to F uniform. Okay. So first we will prove this statement, then we will prove that that's an approximate. Okay. So what we have done is we defined Fourier transform and then took the partial sum. Okay. Using the partial sum by averaging, we took the Cesaro sum and we got this. Okay. So we want to compute this, and we have this condition, that condition. Okay, so we want to compute gn star f, okay, mod minus f gn star f of t minus f of t. Okay, this is what we want to consider, and we want to take the supremum in t and it goes to 0. That's what we want to do. We want uniform convergence. Okay, so this is equal to, let's define the integral 0 to 2 pi. Let me write it and then justify. This is, so gn star f is defined by f of t minus s, then integral gn and all. So this is going to be gn s f of t minus s ds, okay, minus that f of t. But then f of t, so there is a 1 by 2 pi somewhere. Yeah, 1 by 2 pi is here. In the definition, you have 1 by 2 pi. When you define this gn star f, there's a 1 by 2 pi. Okay. Minus, I write just instead of 1, I write this. Okay. And it's f of t. Okay. Instead of 1, I have just written that. Okay. So whatever I have is less than or equal to, I take the modulus inside 0 to 2 pi, 1 by 2 pi, mod of gn is positive, mod of f of t minus s f of t, right? F of t. So okay. Times gn of s ds. Okay. Okay. So now I have some condition, limit something going to for every epsilon. So I split it as two integral epsilon to 2 pi minus epsilon. Okay. So there I have, there I have this term times gns ds. Okay. But then this term is less than or equal to sum of this, mod of this, sum of this. That is less than or equal to the supremum norm of f. So because of all that, I can get this. Okay. So this term will go to 0 because this is a number uniform. Okay, and this term, this will go to 0 uniformly. There is no t anywhere here. Okay. So 1 by 2 pi integral, and here, so there are two. Let's see, in the complement. Okay, in the complement of epsilon 2 pi epsilon 2 pi minus epsilon complement in that region. Okay? In that region, I'm integrating. There are two integrals. I'm just writing it. Okay? This is equal to f of s minus t minus f of t times mod of times dls ds. And this is less than or equal to 1 by 2 pi. I don't care about this. This goes to 0, of course, as n goes to infinity uniformly. I don't care about this. I'm worried about this only. Okay. The second term, is less than or equal to, I take this out. This is supremum of s, we are integrating s in mod s in this epsilon 2 pi minus epsilon complement, okay, mod of f of s minus t f of t, okay, times I have this integral gns ds in this, and gn is positive. Okay, so it is less than that integral, the whole integral 0 to 2 pi, and that is 1. So I don't write it, okay, times 1. This is equal to 1. Okay. I mean, I take this out and then I get the integral over this region, which is less than or equal to integral over the whole of that, and that is equal to 1. Okay. So I have only this. Now this f is continuous in a compact interval. So it is uniformly continuous. Okay. Then this given, I mean, here I should have taken the delta. This should be the delta. Okay. And I mean, this is true for all epsilon. You can choose that epsilon, all epsilon. You can choose an epsilon. You call it delta if you want. You choose a delta such that this is as small as you want. The supremum is as small as you want because it's uniformly continuous. You are taking the supremum. Okay. So this is, I shouldn't write epsilon. Maybe if there is delta, it should be less than epsilon. This goes to, this is very small. Can you fill up the argument? Shall I repeat it? Sorry, you are lost or something. It's okay. I have this. By uniform continuity, you can make this very small. Okay, maybe I should have taken delta here. Okay, then choose very small delta. Choose delta such that this is less than epsilon, independent of this t. Okay. So this will go to, this will be go to 0 uniformly. I mean, it's better you write the argument. Okay? I mean, I just said it, so you convince yourself. Okay. So all we have to prove that this is an approximate identity. Whatever the, incidentally, this is what is called Fejer. I haven't calculated, so I have to calculate what is that. Okay. So let's calculate the sigma n. Okay. So proposition sigma nf at t equal to 1 by n sin square n t by 2 sin square t by 2. I mean, I'm not talking the endpoints. I'm not writing this. Actually, the endpoints. See, even this dn. This is only for t in this 0 to 2 pi, the open interval. Okay? On the endpoint, it will be exactly 2n plus 1. But we don't care about it because we are only integrating it. Okay? So we are not writing what is it in the endpoints. Okay? This is also for t in 0 to pi. Okay? Only in the open interval we are writing this. So this is the claim. dn we have already calculated. This dn we have already calculated. And from dn by taking Cesaro sum, we get this. Okay? So I want to compute this. Okay? Okay. That's all, no? There is no constant. This is right, no? You remember? This is right. Okay. Now I want to calculate sigma nf at t, which is equal to summation 1 by n summation k equal to 0 to n minus 1 this dnf at t by definition. So that is equal to 1 by n summation n equal to k equal to 0 to n minus 1. This term, sorry, this term, and this is just the imaginary part of. I keep the sign 1 by 2, 1 by sine 2, t by 2 outside. And this is just the imaginary part of. I mean, here only we have the n only. Sorry, here, yeah, we have the n only inside. Imaginary part of e power. So whatever that I have, e power I n plus half. Yeah. Okay. This is okay. So this is equal to 1 by n summation k equal to 0 to minus 1. And this is just the, I mean, this is imaginary, but this is just the sum, geometric sum. Okay. And so when n equal to 0, it is it by 2. So I take the sign outside. E power, what is the formula? A into r power n minus 1 by r minus 1, right? So A is e power, I have the imaginary part. So there is no sum. E power I t by 2, right? Times e power I t, right? That is the, and there are n terms. So int minus 1 times e power it minus 1, right? And imaginary part of this. Okay, so I want to get that. Okay, so that is my aim. So first I take this out. I change this. E power, I take this e power it by 2. So e power it by 2, e power minus it by 2. And this is just I times sine it, 2 times I times sine it by 2. So I put 2n, and there is a, then I take the, I mean, 1 by I will be minus I. So I take a minus here, minus 1 by sine t by 2 times imaginary part of, I mean, I get a I times sine of this. Okay. So I take the sine t by 2 outside. So you get sine square t by 2 here. Okay. And here I will get only e power I n t. This is just the real part. 1 by I will get, so I will get an I here. So this is the real part. Okay. Real part of I n t minus. I have taken the sine I by 2 outside. Okay. Like we are going to do the calculations. So this is equal to minus sign is there 1 by 2n times square 2 by 2. And this is just e power, I want to get that n plus half. No, not n plus half, nt by 2. So I take the e power I, the real part of I want to get the e power int by Here it should be n, sorry. It should be n. I mean, this should be capital N. Okay. This is just sine, I mean, you take this and this is just the, yeah, now I get this. Okay. This is equal to whatever I have here times, so e power I n t by 2, then it's bar. Okay. This is just 2, so this is e power I n t by 2 into I times sine of n t by 2. Okay. 2 times right? That is what is this. Okay. And I have a real part. Okay. Now I am multiplying by the e power I n d by 2. This is except I, this is real. You can take this out. Okay. And you have 2i of this, and real part of this, that will be imaginary minus the imaginary part of it. And that minus will cancel with that minus. There is a minus here. Okay. So this is equal to, I write that 1 by 2n sine square t by 2. Okay. If I take, I mean, I have got this, and this is real, you can take it out, sine n by 2. And this is real part of I times, and there is a 2 will also cancel. Whatever the 2 we have, that will cancel with this. I times that e power I n t by 2. Okay. And you get another sign. That's all. That's all. So we got that. Okay. Okay, I could have left it as an exercise, and it's anyway standard. Okay. Now the next proposition is, so whatever we have defined as sigma nf, okay, this n equal to 0 to infinity, that's not n equal to 1 to infinity, because I'm taking up to n minus 1, n equal to 1 to infinity, is an approximate identity. Okay. And proof, I mean, it's clearly sigma n is greater than 0, sigma n is greater than or equal to 0. The first condition is satisfied. The second condition is integral of that sigma, I mean, 1 by 2 pi, the integral should be 1. And notice that the dn, integral 1 by 2 pi, dn s ds 0 to 2 pi equal to 1. I mean, it's not directly clear from that, but this dn is the sum of some e power something, right? That is how we defined it. Sum of e power something. And each of the e power int, when you integrate, that will be 0 except the constant term. And the constant term will integrate to 2 by. Okay. So this is equal to summation minus n to n e power I n t, right? Except 0 term, everything will, if you integrate it, that will be 0. So there you get a 2 pi, and that is equal to 1. So each, now this is sum of the dn, and each one has integral 1, and it's clearly, so this implies integral over sigma n 0 to 2 pi 1 by 2 pi is also equal to 1. Because each dn, it's the integral is 1, so sigma n is sum of that, it's an average of that, that should also be 1. So second condition is also satisfied. So we have to worry about the third condition. So now let epsilon greater than 0. And you want to consider this integral epsilon to pi minus epsilon sigma n. Yep. Huh? 2 pi? 2 pi minus. Correct. Yeah, 2 pi minus epsilon. So it's equal to what? Epsilon times 2 pi minus epsilon. What do we have? We have sine square n t by 2 sine square t by 2. And this is, of course, less than or equal to 1. So we want to, I mean, this is all less than or equal to, this is all positive. So that's 1 by n. So this is equal to 1 by n epsilon to 2 pi minus epsilon. And this is less than or equal to 1. We only worry about this sine square t by 2. And sine square is, I mean, after epsilon it will increase, and before pi minus epsilon it will decrease. 0 to pi it will increase, pi to 2 pi it will decrease, right? So this is less than or equal to 1 by n, and this is just 1 by sine square epsilon by 2. Okay. I mean, you can take, this is all the, I mean, for each t, this is less than this. So you can take it out and that integral is. So this goes to 0. Done. So we have proved that it's an approximate identity. This proved corollary sigma n f converges to f uniform. Okay. Even to SNF may not converges, this sigma nf will converge. This is what is called Fejer's theorem. And corollary to this is if SNF converges, then SNF converges to F. It cannot converge integers. Okay. So we have proved the uniform convergence of Sn when the derivative exists and all that, and it should actually converge to this. We proved absolute convergence, that should actually. So we'll stop. We'll see more about pointwise convergence next.